by our human body and
Okay.
how it is converted into potential energy and kinetic energy.
Okay.
So you read this first part because the body.
Because of the body is an external object and different parts move with different speed, we establish motion of the jumper in terms of the position and velocity of the center of mass, which is the point in the body at which all the mass may be considered to be concentrated. Figure 4.28 show the position and velocity of the CM at different stages of the jump.
Okay, so this is about a man trying to leap, trying to jump up, and the center of mass or the center of gravity where the whole body's weight is supposed to concentrate at this point. So it's called the CM, center of mass, or sometimes it's called the center of gravity.
Yeah.
So this is the point where the mass of the whole body is concentrated. So when this man bend down and spring up or leap up, he try to jump a certain height. So it is divided into two stages. The first stage is when he bend his body until he straightens his body and the feet, his 2 feet is about to lift off from the ground. Okay, so from bending the body to straighten up the body and about to leave the ground. So this is the first stage. The second stage is that his initial velocity, right? His initial velocity as he lift off from the ground is v. So to indicate this is the initial velocity of
Mhm.
the center of mass, it is called VCM. Okay. So from this stage, he's already straightened his body and he lift up until the maximum height. So this is another stage. Now this stage is actually free from the muscle already. His body has already lifted off from the ground. The 2 feet is just touching the ground, right? He spring up until this part. So from this figure until the third figure there, the body, the muscles of the body is no longer contributing any energy, right? So the first stage, the muscle is the one, the body's muscle is the one that acts like a spring, so throw the body upwards. So all
Okay.
the energy comes from the muscles, the chemical energy stored inside the muscle. Okay. So all this energy is also converted to the kinetic energy VCM. So from the this is during the first stage. During the second stage, the VCM, the kinetic energy is converted into potential energy, right? From a
Mm.
lower level to a higher level, right? So these are the two stages. So the second stage is called the free flight. Free flight because the energy, the muscle is no longer contributing energy, right? So it's a free flight. But from the first stage, the extension until the lift off, the energy comes from the chemical energy burned in the muscle, and the muscle act like a spring, pushing up. Okay, so now we consider the velocity now. So earlier on, I explained to you the muscles and the conversion of energy. Now we look at figures. We look at the velocity and the height. Okay, right. From the initial stage here, as he bend the body, the velocity is zero. The initial velocity is zero. Until he is about to lift off, he has a certain velocity, and this velocity is VCM, right? This we call it VCM. So from zero until VCM. Now the distance moved is h. The distance moved by the center of mass is h. So these are the figures that are involved, right? If I want to calculate the average velocity before the lift off, that means from the first until the second figure here, the average velocity during this time, right? So the average velocity is the the final velocity plus the initial velocity divided by 2. So average velocity, initial velocity is 0, final velocity is VCM. Okay, so the average velocity is VCM plus 0 divided by 2. Okay, so this is the average velocity. But we also know that the average velocity is the distance moved divided by time. So the distance moved is h, is the distance moved by the center of mass h, and the time taken is delta t. So we have two different expression involving the average velocity. One comes from the final velocity before he lift off, and the other one comes from the distance divided by time. So we have these two, and we know that the two must be the same. Since both of them are average velocity, the two of them must be the same. So VCM over 2 must be the h divided by delta t. So we proceed to hit this. VCM over 2 is the average velocity. H divided by t is also the average velocity. So we know that the final velocity before lift off is 2h over delta t. So this is
Okay.
the average velocity. When you read this part using the principle,
Using the principle of the conservation of mechanical energy, we can find h, the maximum increase in height of the CM, in terms of velocity VCM of the CM at above. Taking PEI, the gravitational potential energy of the jumper, Earth's distance just as the jumper lifts off from the ground to the B0, and that, noting that the kinetic energy KEF of the jumper at the peak is 0, we have.
okay. Now this second part is regarding the lift off. Now once the both his feet lift off from the ground, he has an initial velocity of VCM. And finally, he reached the maximum height of h. So during this stage, the conservation of energy, we can use the principle of conservation of energy. So the principle of conservation of energy is this one. The equation is this. The initial potential energy plus the initial kinetic energy is the final potential energy plus the final kinetic energy.
Okay.
So, where is it? Okay, right. So the initial potential energy, the potential energy at this level here, this level is 0. The initial potential energy is 0. Then final potential energy at this level is mg times y, right?
Okay.
Okay. Then we talk about the initial kinetic energy. The initial kinetic energy, VCM. Final kinetic energy, 0. Because at the maximum height, the person is momentarily at rest. Okay. So substituting into this equation here, the initial potential energy is 0. The final kinetic energy is 0. So we have the initial kinetic energy equals to the final potential energy. So initial kinetic energy is half mv squared during this position. Half mv squared, right? Half m, the v is vcm. Okay. Then the potential energy is mgy. Mg and the y is h. So the y is h. Okay. So from this equation, we try to make h the subject of the formula. So h is as the subject of the formula is like this. H equals to VCM square over 2G over 2G, right? VCM square over 2G. Okay. Now from the from the experience, from the how to say, from the experience of the average, how to say, those people there, right? The average height here, from the bending position until the straightening position, this height is 0.4 meters, right? It may be, I don't know, this one is not the Asian size, probably maybe European or American, they are bigger in size. So this 0.4 meters from bending to stretching position, the height is the motion of the center of gravity is 0.4 meters. This is their standard. And the time taken for this person to stretch his body from bending position, spring up to this stretch position, the time taken is 0.25 seconds. So this is the estimate. So what is the average velocity then? The average velocity we have found out earlier, VCM is 2h over delta t.
Okay.
So 2h is 0.4, delta t is 0.25. So we know that the average velocity before the lift off is 3.2 meter per second. This one. This is the initial velocity for the lift off. So I better type here, initial, yeah, initial velocity, okay, before the lift off. Okay, so this is the initial velocity before lift off, and they estimate from the height of the average height of those westerners lah, and the time taken is 0.25 seconds. So next we come to how to estimate the height when he spring off like that. How far can he go? How high can he jump? Right? Just leap up like that. It's not run then jump. It's different case. Because when you run and jump, the kinetic energy will be converted to the potential energy from the running part. Now this one is just stretch up like that, purely from the muscles. Right? Okay, so how about the height? Now the maximum height we have found out earlier using the conservation of energy. The maximum height is VCM square over 2G. So VCM square over 2G, we copy down here. VCM over 2G. And where the VCM come from? It come from our estimate here. Estimate of the height and the time taken. So it's 3.2. So substitute into this expression, 3.2 square over 2G. 2 is 2 lah, then G is 9.8. So the maximum height reached is 5.2 meters, this one. So that means when the person stretch himself and leap up like that, the maximum height he can go is 0.52 meters. Okay, so this, the first stage, the energy comes from the chemical energy, and from the chemical energy is converted into the energy stored inside the muscles. So the muscles stretch up, then this person can leap with a certain velocity. So all this initial velocity comes from the from the food, chemical energy converted into the energy stored inside the muscles. And from the muscles is converted to kinetic energy. So this is the first stage. So during the second stage, the kinetic energy gain is converted into potential energy. So this is the calculation for kinetic energy converted into potential energy. From there, we can see how high he can jump, right? Okay, so if this is the height and this is the velocity, how much energy is used up? So we try to calculate the kinetic energy using the formula half mv squared. This one, half m. So he estimate this person to be 68 kilogram, 68 kilogram, and the velocity before the liftoff is 3.2 meter per second. So half mv square is 3.5 times 10 to the power of 2 joule. So actually this is 350 joule. So this 350 joule come from the chemical energy in the body converted into kinetic energy. But this is the useful energy. Useful energy means the energy that is converted into kinetic energy. But actually, the efficiency is not 100%. You read this part, then you will know why it's not 100%.
Because the
Because
muscles are at most because the muscle are at most 25% efficient at producing kinetic energy from chemical energy. Muscle always produce a lot of internal energy and kinetic energy as well as work. That's why you perspire when you work out. They use up to 4 times the 350 joules, about 1,400 joules of chemical energy in one jump. This chemical energy ultimately comes from the food we eat, with energy content this in unit of food calories, and one food calorie equal to 4,200 joules. So the kinetic energy supplied by the food as internal energy and kinetic energy in the vertical jump is only about 1/3 of the food calorie.
okay, there's a something here. Ultimately, okay, right. So this 350 joule we can see from the kinetic energy, but this is not the amount of energy produced by the body. The body actually produce more than 350 joule, because when he work out like this, he perspire, and a lot of energy is converted into heat energy. You see, when the person sweat and so on, his energy is not only converted into kinetic energy, but is also converted into heat energy to heat up the body and cause the sweat to come up. So this 350 joule is only 25% of the total amount of energy generated by the body. The other 75% is generated as heat in the body, and he sweats and
Okay.
perspire. Okay, so instead of 350, actually what he used up is 1,400 joule. Okay, according to the estimate, is 1,400 joule. From the food is 1,400. And this 1,400 and the food, 1 calorie of food produce 4,200 joule. So this one is about one third, 0.3 calorie, right? Because if 1 calorie, they can have 4,200 joule. So by jumping like that, he used up only 0.3 calorie of food. That's what they're trying to say. Okay, next. So we want to find the power. This is the amount of energy useful energy, not the amount of generated by the body, but the amount of useful energy that we can see, 350. So to find the power, we use the energy divided by time. So we use 350 divided by 0.25 seconds. So it's 1400 watt, 1400 watt, and it is equivalent to 1.9 horsepower. So this is the energy, and
Okay.
this is the power of the useful power. Okay. Now, to know more about this human body, you can read this part. So human can.
So human can produce about 2 HP of mechanical power for periods on the order of seconds. Table 5.1 shows the maximum power output from humans for various periods while bicycling and rolling, activities in which it is possible to measure power output accurately.
Okay. So roughly it will be like this. The activity and amount of time consumed and the power and the time consumed is given in this table here. Okay. Maximum power output from human over various period. Okay, so this is the table showing the power.